Yes, we are here to understand what is a new concept. It's called as cognate linkages. So, to understand what this cognate means, let us first understand this terminology, that is the coupler curve. So, here the definition says that each point of the coupler link traces a different path, and that path is called as coupler curve. So, let me explain what it means. Okay, so suppose we are having a mechanism in this fashion. There's the crank and rocker mechanism, wherein the crank is rotating. So the fixed link, I'm going to call it as 1. The crank, we are going to call it as 2. And this link, I'm going to call it as 3. And the rocker, which is going to oscillate, I'll be calling it as 4. So as the link 2 rotates, link 4 is going to oscillate, right? So the connection between this input and output link is given by link number 3. Okay, that's why it is also called as the coupler link. That means it couples the link number 2 and link number 4. So it is called as coupler link. So when this mechanism is simulating or it is working, I can choose any point on this coupler link. Say if I choose this point will trace a particular curve, say like this. Similarly, if I choose another point, maybe over here, this point might trace a different curve. So like this, on this entire coupler link, that is on this entire link number 3, the different points are going to trace different curves. Each of these curves are called as coupler curve. Got the point? There can be a mechanism of this shape also, or this fashion also. I have a crank, then we have a coupler link, then the output link is in this fashion, and this coupler link is not a binary link, it is a ternary link. Okay, so in ternary link we show the hatch lines. So it means now this entire triangle is constituted as a single plate, triangular plate, and if I choose say this point as C, so when the crank rotates, whatever curve the point C traces, okay, the curve might be anything like this. So that curve is again called as coupler curve. So the coupler curve need not be only a binary link, it can be a ternary, it can be traced by a ternary link also. I hope it is clear.
Yes, sir.
Now the second point in this slide, it says that the linkages which trace the same coupler curve are known as cognates. What does this mean now again? So let me draw one mechanism here again. Okay, so let me make this as a ternary link. Okay, so this is our mechanism 1. Now here I have this point C, which is tracing a particular curve of a particular shape known as coupler curve. Suppose we are having another mechanism over here. Okay, and okay, let me change the color now. Okay, this is our mechanism number 2. So what I can see is mechanism 1 and mechanism 2 are having the same coupler point, that is C. So mechanism 1 will also trace a same curve as that of mechanism 2. Okay, so if we are having such mechanisms which are going to trace the same coupler curve, such mechanisms we are going to call it as cognates. I hope it is clear. The different mechanisms which are going to trace the same coupler curve are known as cognates. So that is what is written in this definition. And read it again. The linkages which trace the same coupler curve are known as cognates. Now this is the diagram which I want you guys to draw it now. Or else I'll be sharing you this notes. Is that okay? Do you want to draw it now, or you can refer the notes later?
So we'll refer the note.
Okay. In that case, we can finish the derivation in one class. If you want to draw it along with me, then I might require 2 to 3 classes. Okay. So here, all of you notice that this is a diagram where I've drawn. Let me tell you what is our mechanism number 1. Okay. Okay. So here I'll just highlight this as mechanism 1, and the links I'm going to write it as M, A, B, Q. This is our first mechanism. I hope you can see this clearly. M, A, B, Q. Out of which, let us see how these links are orientated. So link MA, you can see that it is having an angle of theta 2 with respect to the horizontal axis. The link AB is making an angle of theta 3 with respect to horizontal axis. And link number BQ is making an angle of theta 4 with respect to the horizontal axis. All the angles are measured in anti-clockwise. So this arrow should be in this fashion. So all the angles are measured in anti-clockwise with respect to the horizontal axis. Okay, so theta 2, theta 3, and theta 4. And the link AB is the coupler link, but it is a ternary link here. You can see ABC forms the ternary link over here, ABC. So our point C is the point which is going to trace the coupler curve. Okay, so I hope this first mechanism is clearly visualized. I cannot exactly draw it. So MA, A to B, BQ, and this AB is having a ternary link like this. Is it clear? This is our
Yes, sir. Yes, sir.
mechanism. And in this ternary link which we are having, that is ABC, we have mentioned the angles here. You can see the angle between the line AB and AC is given by alpha over here. The angle between AC and AB is given by gamma, and the other angle is given as beta. So this was our first mechanism. So let us see what is the other mechanism here. So I'll just write it here. This is our second mechanism. This mechanism is M, G, F, and O. So it starts from this MG. Second link will be GF till here, and then we are having FO. Okay. So again, here GF is the coupler link, and again, once again, it is a ternary link such that it is having the tip as point C, which is overlapping with the coupler point of the first link. You can see it over here. So point C is again a coupler point for the second mechanism also, MGFO. And once again, in this ternary link also, we have mentioned the angles alpha, beta, gamma in the same direction as we have done in the first mechanism. That means alpha, beta, gamma is written in anti-clockwise direction. I hope you can see here. This is alpha, then anti-clockwise beta we are having, then it comes gamma. Similarly, here also we are having alpha in anti-clockwise beta, and this is gamma. Okay, so obviously since this is a mechanism, you can see that point M and point O are fixed points. Now let us see what is the third mechanism also.
Excuse me, sir.
Yes.
So please explain second again.
Okay. See, the second mechanism is MGFO. Okay. So for a mechanism, you need to have 2 points to be fixed or one link to be fixed. So the 2 points which are fixed are M and O at the top. Can you see at the top?
Yes, sir.
Yeah. And Mg represents the crank, GF represents the coupler link, and FO represents the output link or the rocker. So out of this, you can see that GF link, which is the coupler link, it is a ternary link here, not a binary link. It's a ternary link, that is G, F, and C. And this point C of that ternary link is coinciding with the point C of the first mechanism. Are you getting it? Just like what I had drawn it here.
Yes.
See, in this case I have drawn, right? So this is again same thing, M, G, F. Instead of this O, what I've drawn here, in their case the O has come somewhere over here. Okay, it's the same mechanism what I've drawn. So as usual, alpha, beta, gamma is named. Now let us move towards the third mechanism. Okay, so we are having the third mechanism over here, which is Q, D, E, and O. So Q is over here, which is the fixed point. So QD represents the crank, DE represents the coupler link, and EO represents the output link. So once again, in this third mechanism also, you can see that the link DE is not a binary link, it's a ternary link, and the end point of the ternary link is again point C, which is coinciding with the coupler point of the previous two mechanisms. Okay, and one more point to note is for mechanism 2 and mechanism 3, apart from point C, even point O is supposed to be common here. Okay, so in second mechanism it is MGFO, and in third mechanism it is QDEO. So O is again a common point for these two mechanisms. So again in this third mechanism also, you can see in the ternary link we are having alpha, beta, gamma written in anti-clockwise direction. Okay, and wherever it comes at point C, even here we are getting, see this alpha, beta, gamma written in anti-clockwise direction only. So this is how we are going to draw this mechanism. Now the question arises, what is the reason of drawing this? Okay, what is the reason for drawing this? We know that cognates means any mechanisms which is having same coupler point, it is known as cognates. So in this case, I have got this MABQ, the first mechanism, and MGFO and QDEO. All these three mechanisms are having the same coupler point. That means they are going to trace the same coupler curve. Hence, they are known as cognates. But the question is, what is the purpose of drawing the mechanism in this fashion? Again, the scientist Chebyshev, he has come up with this diagram, and he has proved that for a given mechanism MABQ, for a given mechanism MABQ, there can be maximum two more cognates. Which are those two more cognates? One is MGFO and another one is QDEO. So this is what he has proved. That means for a given mechanism, you can have maximum two additional cognates. Now look at this diagram. point C is covered from all directions. Even if I want to introduce another mechanism so that it will trace the same coupler curve as point C, I cannot introduce another mechanism in this diagram because point C is already covered from all directions. We don't have any scope to introduce another mechanism. So that's how he has concluded that maximum 3 mechanisms together can form the cognates. You cannot have the fourth mechanism. Is this point clear?
Yes, sir.
The same thing, whatever I've told, I've written here. A 4-bar mechanism, MABQ, that's the first one, has C as the coupler point on the link AB. 2 additional 4-bar mechanisms, that is MGFO and QDEO, with the coupler point C, trace the same coupler curve. This is what we have written as the explanation. Now, how these things are constructed? Remember, these construction steps, you need not to follow them exactly to draw this. You can draw a rough diagram over here to explain the cognates, but we need to understand how these constructions are done. So the first construction is, they're telling that we need to draw the parallelogram MACG and QBCD. That means they're talking about, let me clear this. So the two parallelograms which they are talking about is, I'll write it down here, MGCA. Okay, so this is one parallelogram, you can see MGCA, and another one is QBCD, that is this one. We need to draw these two as the parallelograms. If they are parallel, that means you can see here line GC will be parallel to line MA and also equal to that. Similarly, line MG will be parallel and equal to AC. Okay, I'm talking about this parallelogram here. If I come to this parallelogram, then what we can write here? CD is parallel and equal to BQ. CB is parallel and equal to QD. Is it clear now? The first step. We need to ensure that these are the two parallelograms. In the second step, return to construct the triangles GCF and CDE similar to CAB. Let us see what does it mean. Just clear off all these lines here. Okay, so you can see the center triangle or the ternary link of the first mechanism here. It is CAB. So they are telling that in the second step we need to construct two more triangles, that is GFC. This is our second triangle over here, and third triangle is CDE. This is our third triangle, and all these three triangles must be similar to each other. See, when I say similar to each other, means I can have this ratio. Like for example, if I take the first triangle, I'll take the ratio of the two lines which are subtended by an angle of alpha. That is nothing but AC upon AB. Can you see this? In the first triangle, for alpha is subtended by AC and AB. So this ratio must be equal to, in the second triangle, alpha is over here. The two angles which are subtended by them are GF and GC. So it will be equal to GF upon GC. This should be equal to, if I come to the third triangle, alpha is over here. So it is CE upon CD. All these ratio must be constant. This is the property of similar triangle. So I hope this step is also clear. They have said that we need to draw three similar triangles, CAB, GFC and CDE. Since they are similar, I have just taken the ratio of two lines subtended by alpha degree. So I have got AC upon AB for first triangle, GF upon GC for second triangle, and CE upon CD for third triangle. All these ratios are same, hence I'm equating them to constant K. The last step is to construct another parallelogram OFCE. So in this diagram, it might not look like a parallelogram here. So they are talking about this one. Okay. So this is a parallelogram which they are looking for. OFCE. So in my drawing here, OE and FC are not parallel. But since it is a parallelogram, then we have to write that OE must be parallel and equal to FC, and OF must be parallel and equal to CE. So this will complete our construction process. Two parallelograms, three similar triangles, and lastly one more parallelogram, that is OFCE. Okay, once these constructions are done, then they have written here that MGFO and QDEO are the two possible cognates here, which we have already seen. MGFO is our second mechanism and QDEO is our third mechanism. Is it clear? Now we need to prove that the second mechanism and third mechanism will also trace the same curve as that of the first. That means we need to prove that these both are cognates. So already the first mechanism is known to us, MABQ. If it is known, means I know that point M is fixed. I know that point Q is fixed. So for this mechanism, I need to prove that the other two mechanisms are cognate. The other two mechanisms can be cognate only if point O is fixed. So in other words, or in simple words, I need to prove that point O is pivoted or it is fixed at that particular position where I'm showing it in the diagram. If O is fixed, automatically the mechanism is drawn in such a way that C will be common for all the three mechanisms. So let us see how to prove that point O is fixed here. That will be the proof for the cognate linkages. Before again proceeding with the proof, there is one more concept called as Cayley's diagram. I'll just write it here. Cayley's. It is Cayley's diagram. What is this Cayley's diagram? So he has again simplified the same diagram just for the sake of derivation. So you can imagine now, if I hold this point O, and if I stretch point M and Q horizontally, that means I'm going to stretch M in this direction and Q in this direction. If I stretch them, then this point A will come on this horizontal line and point B will also come on this horizontal line. So how this diagram will look when we do this, let us see. Over here, we have maintained point O. I have stretched M and Q such that A, B will come along the straight line. So our mechanism now, this is our first mechanism, MABQ. This becomes our second mechanism, MGFO. And this becomes our third mechanism, QDEO. Okay. So accordingly, we have mentioned all the angles also here. Okay, this is just for reference, Cayley's diagram. Just in the proof at one particular step, we'll be using this diagram. Okay. Let me know if you have any doubts till this step so that we can proceed with the derivation.
No, sir.
Great. Here we have written uh, the first step of the proof is using cognate constructions. We have located pivot point O. It is now required to prove that this point O is stationary in order to have these two cognates. So let us see how we are going to prove this. Okay, so I have this diagram with me. So first step, I'll write down the properties of the similar triangle like what I'd written before. So let me show you here. This is the first triangle. This is the second triangle. This is the third triangle. Okay, so I'll take the ratios of those two lines subtended by the alpha values, that is AC upon AB in the first triangle must be equal to GF upon GC must be equal to CE upon CD. All these things I'm going to write them as a constant. So this is my equation number 1. Okay, now let us refer the Cayley's diagram here. Look at this Cayley's diagram. Can I write the summation of link lengths of MO equal to MG plus GF plus FO? Is it correct? As per this Cayley's diagram,
Yes, sir.
MO can be written as MG plus GF. Let me bring this also in the whiteboard here. Just for our reference sake. So the second step, I'm going to write it as MO should be equal to MG plus GF plus FO. Okay, this is our equation number 2. Now I just need to convert this all MG, GF and FO. So let us see how best we can convert that. So look at this parallelogram in this diagram. Look at this parallelogram MGCA. Can you tell me what will be Mg equal to? In terms of link length.
AC.
Exactly. So MGCA, it is a parallelogram. So Mg will be equal to AC. So I'll write that here. Mg will be equal to AC. And what is AC equal to as per the equation number 1? AC is equal to K into AB. Agreed?
Yes,
So
sir.
just write this as one equation. Now for this Mg, I have used some conversion. Let us see what conversion I can use for GF. GF is directly available in equation number 1. So what I'm going to do is I'm going to write here GF will be equal to K into GC. This is directly available in equation number 1. Just a minute. Okay. Now look at the diagram here, and can you tell me what will be GC equal to as per the parallelogram MGCA? What will be GC equal to? We should have
MA.
line and this line parallel and equal. So GC equal to MA. So I'll just modify this equation. I'll write GF equal to K into GC is MA. So this is my second equation. So let us now identify what is this FO. So look at the diagram again. FO should be equal to what? As per the
CE.
as per the
CE.
parallelogram, so FO and CE must be parallel and equal. So I'm going to write FO equal to CE, and from equation number 1 I can write CE is equal to K into CD, right? So this is K into CD. Okay, but again, what is this CD equal to now? As per the second parallelogram, CD is equal to what? You can see here, this is CD. This should be parallel and equal to
Q, QB, sir.
yeah. So I'll write this FO equal to, once again, K into, instead of CD I am going to write it as BQ. So this becomes my third equation. I hope this step is clear. Now we have written the values for MG, GF and FO in terms of the constants K. Now let us write again all these values once again in terms of the polar notation. So I'll write here in polar notations. So first thing is we are having Mg. Mg what we had, I had got it as K into AB here. Can you see this? Mg I had got it as K into AB. So I'll first write it as it is. Mg was equal to K into AB. Now this I need to convert this into polar notation. So let us see this line AB, this AB, whatever I've written here in the diagram where it is. Over here. Okay, just a minute. AC. Okay, I'll just rectify this here. In polar notation, I will first write what Mg is equal to. So you can see here in this diagram, this Mg, can you see the parallelogram and tell me Mg is equal to which line?
AC, sir.
Exactly. MG will be parallel and equal to AC. And what is the angle or orientation of AC with respect to horizontal?
Alpha plus Q3.
Alpha plus theta 3. Right? So whatever I had this K into AB, this component is making an orientation of alpha plus theta 3. So in polar notation, if I want to write, I'm going to write it as K into AB e raised to j alpha plus theta 3. Okay, I'll write this as equation number A. So mg is over. Now let us come to gf. Okay, where is this gf? Okay. So can you tell me what will be the orientation of this for gf? See, gf is making an angle of what? Alpha plus theta 2,
Theta 2.
right? So in polar notation, I'm going to write it as it is here. That is gf will be equal to k into gc, which we had the equation, e raised to j alpha plus theta 2. So this is my equation number B. Last one was FO. So what I'm supposed to write for FO, it is K into BQ. See, this BQ is parallel and equal to CD, right? You're getting this? So just like what we have written here, that is alpha plus theta 3 and alpha plus theta 2, this will become as alpha plus theta 4 here. Okay, so this angle is alpha here. So the total orientation will become as alpha plus theta 4. So this will be K into BQ e raised to j alpha plus theta 4. This is my equation number C. So now all these three equations, that is A, B and C, I am going to substitute in our equation number 2 here, the main equation. Okay, so let me write that main equation here. What we had is MO is equal to MG plus GF plus FO. So we have these values here. K into AB e raised to j alpha plus theta 3 plus K into GC e raised to j alpha plus theta 2 plus K into BQ e raised to j alpha plus theta 4. Okay. So out of these equations, what I'll do is I'll take out K into e raised to alpha j as common. So what remains inside? The first term we have AB into e raised to j theta 3 plus GC into e raised to j theta 4 plus BQ into e raised to j, sorry, this is theta 2. This is theta 4. Yeah, I hope this step is clear. Now in this equation, I'm going to just replace one terminology. You'll understand this later why I have done that. That is this GC. So let us again look back to the diagram and see what this GC is equal to. So in the parallelogram, again I have GC equal and parallel to MA. So I'll just replace that GC by MA. I'll do it here only because I'll be giving you the notes. So I'll edit it here only instead of writing it once again. So instead of writing GC, I'll write it as MQ into e raised to G theta 2. Okay, so this AB into e raised to J theta 3 in polar notation, AB into e raised to J theta 3. If I want to convert that into back to the vector notation, what it becomes? It becomes just the line AB.
Sir, I have a
Sir.
small doubt.
Yes, sir.
Sir, that
Sir,
is
it should be
MA, sir,
sir.
not MQ.
Yeah, I was doing that only. It is MA, right? Okay. So AB into e raised to J theta 3. If I want to convert this from polar to back to vector, so this becomes only AB. Similarly, this becomes only MA, and this becomes only BQ. So what is this AB plus MA plus BQ? Let us go back to the Cayley's diagram over here. MA plus AB plus BQ, it becomes as MQ as per the Cayley's diagram. Clear? The horizontal line. MA plus AB plus BQ, it becomes as MQ. So we are having the same equation here, MA plus BQ plus AB. So this becomes as MQ. Okay. So what we have started is MO equal to, and this is what we have got. Is it clear? So again, e raised to alpha j of MQ, it is still in polar notation. Let me convert that into again vector form. So it simply becomes the vector MQ or link length MQ. So I'm going to get MO upon MQ as K, or in other words, it is a constant. Okay. So this actually is a proof. Now from this equation, how can I conclude that point O is stationary? So look at the individual terms. I am having this M over here, also M here and Q here. Okay. So if I just look at this M and Q, they are already fixed. M is fixed, Q is fixed. Okay. So in this entire equation, I have M which is already fixed and Q is also fixed. Only remaining is O. So if this at all has to be a constant, then obviously point O must also be fixed. If point O is varying, then this can never be a constant. Okay, if this equation has to be constant, then point O has to be fixed. That is how we can conclude from or interpret from this equation. So from the above equation, I can clearly say that point O is fixed. Okay, so this is the derivation. So the derivation seems to be very simple, but unless you solve it a couple of times, it will lead to a lot of confusion here because the diagram is complicated. So what I'll do is I've prepared the notes for this. I'll scan it and I'll send it to you. You can go through this derivation. And if you have any doubts again, we can clear it in tomorrow's class. So again, tomorrow's class exclusively, I'll be dedicating it only for the doubt clearing session. So I'll share the notes now immediately. You can just go through it. And if you have any doubts, please come back tomorrow. We'll sort it out. Done?
Okay, sir. Thank you.
So we'll wind up the class now. Thank you.